Hello, circuit number 6 now. This is the traffic light controller using logic ICs. It's a good training circuit for digital electronics. Here you can see the main circuit controller. This is the heart of the switching of the circuit, or switching of the lights. As you can see, we have here the usual 4017, the Johnson counter, and then we have our lovely timer, the 555 timer circuit, and for each side we have 3 timers, 1, 2, 3, and then the other side the same, plus or minus. You can see that it's a repeated circuit. This one, the 4017 counter, and then the 3 timer circuits. So this is our main control. Yeah, so this traffic light controller is 4 circuits. First is this main controller. There is, as you can see here, the HMI, which is the human machine interface circuit. I'll briefly show you here. This is another circuit which is attached to this whole circuit for human interface, where you actually input instructions to the circuit so that it behaves in a certain way. And then there is the manual control, which now is interfacing the main controller and the HMI. And then there's another circuit. We'll make a description of it. And then the 4th circuit is actually the pedestrian circuit. This now is the circuit that runs the pedestrian lights out. Now, as usual, we go to our script. We must read the script. For those who have not been following our previous circuit descriptions, this is the script that we always been reading for warning signs, for the philosophy of these circuits. So EWB, electronic waste benefit, is our philosophy. We intend to use as much waste as possible. Please use as much waste as possible from electronic equipment, be it radios, televisions, industrial machines, or home appliances, or any discarded electronic equipment. You find components there that you can use. So as always, safety comes first. You must actually be someone who has experience in working with electricity, and we expect that you also have prior knowledge of electronics, and minimum age of 10 years. I don't think you will actually be okay. Under 10 years, it's very tricky that someone would actually understand the concept that we are going to discuss here. So, as usual, your workshop, your equipment, please, no children, no kids under maybe 10 years, 9, 8, 9 maybe, but I would say, through my experience, 10 years and above would actually do. And then please note, this is not a electronics training lesson. There is a lot of literature on electronics. Please do that before you actually attempt these circuits, because we are not going to describe components, how they function, we are just going to actually make a description of a circuit, how it works, so that you can build it and modify it. You can adapt it to suit what you want. You can improve it. You can whatever you do with it, benefit from it. That's why we expect that you have your prior knowledge before you actually attempt these circuits. The philosophy, of course, always use recycled equipment, recycled components. So we expect that this circuit will actually benefit in training, will benefit in not in at home but for industrial use. you can actually use this circuit in schools and actually build a working traffic light controller where you can use for kids to cross a road. Now, the required resources as usual. Well, this is not a programmable system, so no programming at all. The computer might be there just to create printed circuit boards or to redraw the schematics, but otherwise no programming. It's a straightforward digital logic circuits that you populate on a pre-made breadboard, or you populate on a veroboard. I've populated this circuit on a veroboard. Well, it's tedious, but you learn whilst you are doing that. So a soldering iron, of course, the meter, the tools that you need, oscilloscope, maybe not, even the logic analyzer, you may not need that. Software, because this is not programmable. Well, no programming at all, no ladder, no flow code, but Proteus or any other schematic drawing suit that you may find, or PCB making suit that you can find from the internet will still be okay if you want to improve it or to make some changes on the circuit. So as usual, your time, your patience, your passion, your dedication. Thank you for taking your time with me. Enjoy this circuit. Now, where do we start? As far as the circuit is concerned, our logic circuit, I would want to start where I would explain the timing function, which is the main building block of the timing factor, to explain how this circuit works. As you can see here, I've just drawn it so that at least it's explainable, it's feasible. If I had to include all the components here, yeah, it will be difficult. It will be more like too many components on one sheet or one schematic and end up confusing. So this is more like in block form, but it's a circuit that you have to build. And then this main board controller, which I call the logic board, it's got attachment to other boards, so it has external attachments to it for it to work. Here is the relay driver. You connect your relays here. This is the ULN 2003, 2004, 2803, 2804, or you can actually do it with separate transistors, but this is the best. It's smart, it's clean. You connect your relays here, and the relays can be 12 volt, can be 5 volt, depending on the relays that you get. Otherwise, you get the relays that will actually be working DC. They must be DC. So if it is a voltage higher than the control voltage, which I actually recommend that you use 12 volt for the control. You can use 24 volt if you get 24 volt relay. You can actually put your 24 volt here, but separate it from the power of the control circuit. So this is the nice thing about these relay drivers. You use different voltages. The relays will actually come in because this just goes low and operates a relay. Right, where do we start? We are going to start with timing circuit, and we're going to use a simulation as well so that you see exactly what is happening. And then learning the timing circuit, then you understand how this circuit will actually function. Right, let's go for the timing circuit. Here is our timing circuit. Let me try to zoom it if I can, so that at least we see what is happening. Okay, right, now I think it's zoomed properly. Now, yeah, so here we have our relay driver. Now this relay driver, now we are using it as a transistor driver. We are actually using the internal transistors here that you actually drive using a power input here, and then when you put a positive at the input, the output as you can see, yes, number 1B and number 1C. It actually switches on a transistor to ground this part here. So our main timing circuit is the monostable oscillator, or the monostable circuit, using the 555 timer. You will find that you can also use the dual 555 timer, which is the NE556. The NE556 has got these two timers in it, and two power pins of like number 8 here and number 1, which is power here, a positive, and ground here. But the NE556, or a different version of it, I think it's the MC3403, if I remember very well. It's also the same IC, but made by Motorola, if I remember very well. There is another 555 timer, the dual one, in a different number, but the same IC. So this is a monostable setup. So what happens is, you have here a transistor driver, which if you put in a high at the input, it draws a low here, and the low is transferred to the timer, which is a trigger input. When the trigger input goes low, the output goes high for a given time, which is actually set by R1 and C1. Remember from our locking system, the electronic lock. If you have not watched that one, okay, you can actually search for it and see how I've actually described it. So this output number 3 will go high for a given time, determined by these two components here. Normally this is the adjustable one that you actually adjust. Sorry, excuse me. And then that high actually is clocking this 4017, just like we are doing it in the E-lock version. The LED and this resistor is just to show the different modes that you can actually use to clock this counter. So this counter is actually clocked only when the pulse that is coming here, because it's now a pulse, is going from high to a low, or it's going from a positive to a low voltage. So we have a pulse that comes at the input, and then the output goes high, and then after some time goes low. If it goes low, that's when this counter changes the output from the previous position where it was to the next. So it's counting from Q0 up to Q9, and then goes back to Q0. So it resets here, and you will see that when it reaches Q5, or pin number 1, the carry out pin number 12 will actually change to low, and then after it reaches Q9 and then resets, carry out pin number 12 will change to a high. So this, though we are not going to use it at all, we are not going to use this function, because we are only just going to count from from Q0 up to Q4 on our circuits, right? So now our timer is the main building block for the traffic light controller. This is the timings that you can adjust to the seconds that you want for each side of the road to be green. The red time and the amber time is normally fixed, but the green time you can adjust by adjusting this capacitor here, the value of this capacitor. If you fix the value of this capacitor, maybe you fix to 15 seconds, then you will just use one capacitor, but you can actually use switchable capacitors, like you connect an array of capacitors and use switches to actually put in or remove capacitors, a combination of capacitors, so that you have different capacitances and different times of the pulse, because the pulse determines the time the counter is actually going to step. So let's simulate, and then you will see what happens. This resistor and the LED is just to show you that if I press here, the output will go low, because if you get a low here, that LED will light up. If I continue pressing, this light will continue to be on, but this one will only come as long as the duration of the pulse here. Okay, let's go for the simulation. Right, because normally when you switch on, the power of the ICs is in any position, so this timer output will be high when you just switch on or when you just power the circuits, and then it will go low. That's why it is stepping to number 2, but that's not an issue to worry about much. So if I press here, which will be a pulse, you can check that the moment I press here, this one will come on and this one will come on and off, and it steps to number 4. Then if I press here, steps to number 7. I press again, steps to number 10. Remember, when I go to number 1, QCO, which is pin number 12, goes low. Right, step that, you see now it changes. And then now I'll show you what I mean by if you continue pressing here, what happens with this LED. It stays on, but this one will just come on and off. It will not remain on. It's because this is a monostable circuit. Right, so I continue pressing. That D1 is only gone on and gone off, but D2 is still on because I am still activating the switch. If I release, D2 goes off, but nothing happens here because it has executed that function. So this circuit here is the main timing circuit. That is the main timing circuit, including that IC. The IC, you will find that now I put it as an actually in the main control circuit. Sorry, it's actually looking like this. It's the one that I put in like that, right, with actually here a negation, negative, like a NOT gate. Okay, yeah, I'm just trying to play around here. Okay, right. Right, if I can move this one to the okay, anyway, no, that's not necessary. Okay, not necessary at all. All right. Okay, now so what I was talking about was this circuit is actually the main building block for our controller. So we have the transistors here, and then we have the timing circuit here, and then we have the stepping circuit here. So this now will not have a manually controlled input switch like this. The circuit will actually step itself. You see that the timers themselves will actually step this clocking circuit by themselves. When we have an output from one of the timers, that output will actually be transferred back to the counter to step it to the next position. Whether the timer that is stepping the counter is from within the same side or from the other side, or you will see how I've constructed the circuit. So this is the circuit, the building block. You understand this first, and then Everything else is now simple as long as you understand this circuit. I hope you see what I mean. Right, let's go back to our logic circuit. So here is our circuit for the timer. You'll see that this symbol here that looks like a not get, it's actually the 200, the UNLN 2003, which is that's part here. This one, it's the inside of that one. It's represented by this one now. So you have that transistor, you have the timing circuit, and then you have the counter. So it's that ULN, the transistor driver, the timer, the 555 timer, and then the counter. So that is our timing block, building block as we have described it, those three components. The switch is not there because the switch is actually this output here, which will be transferred to the input. Remember, the input is going on the enable pin for the counter. It's not going to the clock, it's going to the enable pin. The clock input is wired straight to the power supply, pin number 16. So it's configured to actually step on the trailing edge as I have described in the E-lock circuit. So you have the transistor for triggering the monostable timer, and then you have the counter responsible for stepping, for switching the lights, and then the counter is wired straight on to the relay drivers for light output. So this is side number 1, and then this is side number 2. You will see that this side and that side pretty much the same. The diodes, the purpose of the diodes are working as OR gates. These are OR gates. You can actually replace these diodes as an OR gate. Like if you check this diode number 6 and this diode number 8, if you have a high here at the anode of D8 and a high at the anode of D6, it means here where the cathodes are connected is a high. If you have a high and a low here, still you have a high here. If you have a low and a low here, then you have a low here. And make sure where the diodes are connected, you never leave input for logic gates or combinational logic systems as open ended. You must tie inputs to a certain potential, because the diodes are directional. You must make sure that you put a resistor like what I have done here, that the input here, the clocking input, is actually wired to 0 ground through a resistor. And then this one, this resistor wired to ground, is actually for pin number 13 of IC1. So how does this circuit work? Remember our simulation. If we have a high here at the input of the relay driver, which is this one, it's just one circuit, because each relay driver is 7 circuits or 8 circuits depending on the relay driver that you choose. Get data sheet for these circuits. We are not going to explain much about them here. So if you have a high on the output of pin number 3 of this IC number 1 Q out, if you have a high here, it means this high will actually trigger the monostable, and then the monostable output becomes a high. The time duration actually determined by the circuit, the monostable circuit. Remember our simulation. Here I've just indicated the capacitor value that you put in. This is the values for the capacitors for different circuits, because these timers now represent the lights themselves. So the top ones, IC4, is actually the red output. Then the middle one is the green light, for the green light. The bottom one is for the amber light. The same with the IC4017, the counter. The first output is for the red, the second one is for the green, the fourth one is for the amber. So as you can see where you wired, they are wired straight there, so you must connect the relays according to that. So now the timing of the output is determined by that setup here on the capacitor. Remember, the capacitor that is responsible for timing, and that capacitor from the circuit that I've built, we are looking at 1 micro. I'll show you the value of the circuit, of the components around this timing circuit. We'll actually do the timing circuit as well. So this now high is now transferred to there. It can't go there because the diode is blocking. For now, maybe let's leave out the attachments here. So it goes here, not there, and it's tied to 0 there. If there is a 0 on the end of the diodes coming there, and then it comes to the enable, which is the clocking input for that IC. And remember, when you power the circuits, they take any position, but I have made sure that once you power them, each IC, these two ICs, and each of them actually reset the other. Okay, we'll see how that will work out. Okay, so that high comes here, and well, as long as it is high, it will not affect the counter. The moment it goes down to low, remember, okay, before then, you see that line here coming here, it can't go there because there's a diode. Okay, it's blocked. So where there's a diode, it's blocked. It only comes to the enable there, so it's sitting there as a high, and then it goes down to low. When it goes down to low, this one, because the moment you switch in and switch on, they actually go on position number 3 as outputs. So whichever starts, okay, because this one also actually, if there is a high on output 3 here, this will also will be timing, right? So this one will be timing. So when this one is actually timing, this one will actually come here, and then will actually step to what? To when it goes low, this one will actually step from number 3 here, goes to number 2, right? As you can see, if it goes to number 2 here, follow that path. Okay, we ignore this path first. Okay, it's going up there, but I want you to come back through here, right? Number 2 is coming here, it's coming there, it comes there, and it resets this IC. So whichever starts to count, or to count to number 2, will actually reset the other one. So what are we saying? We are saying if this one starts to go red, and then actually this one goes down from high to low, it means this one will actually step, and then when this one steps, it actually resets this one. So we have assumed that this one is the one, this side is the one that actually starts to go down. So this one will actually go from high to low and step this one to number 2. When this one steps to number 2, it will reset this one to back to high. So it's reset here. So as long as this one is in number 2, this one is reset. So whether this timer was going to go from high to low, it will not affect anything because the IC is reset. So no change here. So this one is not going to change. It's going to remain on number 3 because it's a reset. Now this one is on number 2. Now it goes down again. Okay, let's see. This number 2 is going down to actually operate a relay here as green. So remember, number 2 is green here. This one, number 1, is red, which is kept reset at number 3. So it's actually giving a red. It's operating a red relay, and this one will operate from red relay to actually green relay now. And then it goes up. There are circuits attached to this, which we'll discuss on different video clip. It goes up, comes back through here. So it goes up on 4, comes back as number 5, depending on the condition that the other circuits will do, but it will come back in number 5. Let's suppose this one is looped straight on, comes back in number 5. It has gone high, so this one high. Remember our simulation circuit going high here. We'll actually stop this one and trigger this one, and this green timer, which is the middle one. Remember, the middle one is green, will go high at the output, and it goes high at the output. It goes out is high. Here is blocked, you can go. Here is high, you can go through. Here is blocked, you can go through. Here is blocked, you can go through. It comes back to that one again, to the same clock, and then here back. Remember, it can go, it's blocked, so it will be high here until this timer, which is determined by the timing circuit here, which is that capacitor and the resistor. So after some time it goes low and clocks this one, so it's clocking this one to number 4 now. Let me zoom a bit so that you can see it clocks to number 4. Number 4 now is the third position. Third position is our ember output. Third position is pin number 4, our ember, driving an ember relay here. So it has moved from the green relay to ember relay, operate ember relay, and also the ember, remember, it's coming here to the timer again, a high here, trigger the timing circuit, and the timing circuit goes output high, determined by the timing of the capacitor here, high. Then that high comes again to that, and remember, here there are diodes. It won't go, that one won't go anywhere. It won't go there, it won't go there, it's blocked. They come back again to the same input, the clocking input. Right, the ember time lapses, and then it steps again. So it's going from high to a low. When it goes to a low, it steps to position number 7 now. In position number 7, as you can see, after the ember timing, this output goes through this diode, comes here, can't go there, but comes to the reset pin. So it resets this counter. When this counter is reset, remember when it was on number 2, this one is reset, it's on number 3. So this one is reset, and this one is reset. It goes on number 3 as an output, as high. So when this output, it was low, and then it goes high. So you have a high now here, and this one high. Remember our timing simulation. Our a high here will actually trigger this timer, and output here goes high, goes there high. It can go there, is blocked, and here we follow. Okay, here is just a clamp to ground through a resistor, so you maintain here a high. Here it can go, it's blocked, comes here, there, and enable the input. Here can go there, it can go there because it's blocked, so comes to the enable input. So that time for the red lapses, so it's coming from a high to a low. It clocks now this counter to position number 2. So it was red, and this one is on red, number 3. This one now is now changing from red to number 2, which is green. So number 2 here, output here, comes here straight in, resets this one, keeps it on number 3. It's a reset. and also goes out number 2 to operate a green relay. Number 2 is green, so it operates a green relay. And then the other goes to the attachment circuits. Let's suppose that attachment circuit is not there. We loop number 1 and number 2 here, comes back here as high. Remember, number 2 is high, goes out to the circuits that we'll describe later, comes back here depending on the condition. Is number 2 input a high here, and then a high here, trigger this one, goes high here, because it's a timer determined now by the timing of this circuit here, which I've used 6.8 microfarads for my example. So this one goes high for that time duration determined by the resistor and the capacitor. Output high goes here, it's blocked, can't go, but here through this diode, here it's just clamp, then goes here, remember diode blocking, and then to enable, remember here it can go blocked again, enable there, and the time duration lapses from the green time from high to low, steps again to number 4. Number 4 is the ember, the same procedure. Ember number 4 drives the ember relay. Number 4 again also number 4 comes here to this one, the driver high, and a low pulse comes here to trigger this timer for the ember now, and then this output goes high for the time duration of the ember. Here comes back to the input, the strobe input or the clocking input of that IC. Here it can't go, it's all blocked that side, so it's going to clock this one from high to low, clocks to number 7. Number 7 comes back and resets the counter. And the counter is reset, goes to from amber now to red, and remember this one is still red, and then the cycle starts again, a red here, another like that. So this is how it works. Basically simple as that. And then these attachment circuits are actually just there to control how this, because you can actually interrupt the operation of that. Like here, I was saying from green it goes out, comes back here, and we just loop here, but it's not just a loop. Sometimes it's coming through here, or it is coming through number 3. The same with this one. Number 2 goes out as 4, it can come through as 5, or it can come as 6. Let's take an example of coming back as number 2. As number 3, because we have done number 2, coming back as number 2. So if it's coming back as number 3, because now it's not coming back as number 2. Number 2 still remains as low, so this one is not going to be triggered, or the monostable is not going to work. So if it comes back as number 3, here's a high. The high that is number 2, this high comes back as number 3. Let's maintain a high here. So you have a high here, a high can't go to this one, is blocked, but it can go through here. So you are now controlling this high, the time of this high, which is coming through number 3, just the same way this timer was going to control. So number 3 comes as high, goes there high through that diode, I think it's D5, and then comes here, the other sides are blocked, comes here, and then maintains a high. The moment you take out that high, this will clock to the next from green to actually amber. Now that high goes out, so it's now amber, then amber is the automatic the automatic operation takes over. So the amber time comes out, lapses, and then goes to pin number 7. Pin number 7 resets the counter and goes to number 3 as high, and then next time this one was high and clocks this one and goes to green again. And then if it is coming through number 6, the same here, 6 high comes here, then comes the I think this diode is a repetition. in my opinion. This diode is not supposed to be there, because even if you are going to have a high passing through here straight, it's blocked there, it's blocked there, so that diode is a repetition. You don't need it. Yeah, you don't need it. So if that high comes here, then comes here and clocks that one, then it clocks to number 4 amber, then the amber time count takes over, comes back, and it goes to red by resetting this, and then when it goes to resetting this one, that timer for the red, remember, comes and actually clocks there. So yeah, pretty much described what is happening with the attachment circuits. So when we are going to see what's happening with our attachment circuits, then yeah, you understand basically what's happening here. This is the circuit. It can work as is. If you would want, you can just short these two here and leave out number 3, leave out number 6, and short 4 to 5, short 1 to 2, and the circuit is working perfect. The lock LK1 and LK2, you can actually also leave out. This circuit will work normal. It's a normal switch without any interference. Once you power it, it runs. Yeah, then you can't do much to it, because if you leave out these attachment circuits, then it will just run. Right, that's just about it. I think our clip is very long, but anyway, we'll actually go and describe the other circuits on other clips. This is part number 1, so I'll have part number 2, part number 3, part number 4. I'll see our main parts this circuit will actually comprise of, but a very good learning circuit. So yeah, feedback as usual, dauramireme@gmail.com, and I thank you for your time.